Hey everyone, I am Miss Hu, your physics teacher. In this video, I will be discussing the answers to a past year question and then we will compare the answers to the mark scheme. For some questions, the answers will be covered first so that I can explain the thought process of getting to the answers, as you will need to know how to get the answers and not just what the answers are. Then, based on the mark scheme, I'll explain why the marks are awarded as such. Question 8. Figure 8.1 shows a diagram of part of a simple AC generator. So here's the diagram, and yes, it doesn't quite look like the typical generator that you have seen in your textbook or in your notes. But just because it looks different doesn't mean you can't solve it, because the AC generator is pretty much standard in terms of your syllabus. So A1, identify components A and B in figure 8.1. If you look at the diagram, it's just a variation of the generator, which I'm sure you've seen before. So you have the magnet here, the coil of wire that's going to spin between the magnets, and it's connected to two rings which are labeled as B. So in a simple AC generator, the two circles which are B are obviously slip rings. A is the component that connects the slip rings to the external circuit, and the name of that component is carbon brushes. So let's check the mark scheme. Yes, A is carbon brushes. They will accept the answer if you just wrote it as brushes, even without the word carbon, because nowadays a lot of the AC generators don't actually use brushes made of carbon. Some of them do use metal strips as the brushes instead. B is slip rings, and you can see that the word slip is underlined. You must have the word slip, and you can't just write rings in your answer. So that's how we get the 2 marks for this identification. 2. Component C is made of soft iron. Describe the effect of this component on the generator. So C, which is in the middle of the coil of the wire here, is made of soft iron. It's not a complicated answer. Basically, you just need to explain why we use soft iron inside this coil of wire. And the reason why we use soft iron when it comes to anything to do with magnetism or electromagnetism is because soft iron is great as a temporary magnet. But you don't write that here because the question's not asking you about what's so great about component C. It's asking you to describe the effect of this component. So soft iron, in addition to being a great temporary magnet, it's able to increase the strength of the magnetic field. So that's why we use soft iron. That's the answer we're going to write here. Increases the strength of the magnetic field. In this case, we can specify that it's of the magnet because there's a magnet here. So the soft iron is able to increase the strength of the magnetic field and able to increase the efficiency of the AC generator. So let's look at the mark scheme. Strengthens the magnetic field of the magnet, which is pretty much the same thing as what we said here. So that's how we can get the 1 mark for this question. Question B. The coil of the generator rotates at a constant speed of 2 complete revolutions per second. Sketch a graph of the EMF generated against time on the axes in figure 8.2. The coil is in the position shown in figure 8.1 at time equals 0. So what you need to draw here is the voltage time graph for an alternating current, and that kind of graph is a sinusoidal wave. But you cannot just randomly draw a sinusoidal wave because you have to match the graph to what is shown in figure 8.1. So let's look at figure 8.1. We can see that the coil right now is parallel to the magnetic fields of the magnet. Because the magnets are here, it doesn't matter whether north is on top or at the bottom, the magnetic fields are vertical. The coil of wire is also vertical, which means that it's parallel to the magnetic fields. Now remember that when the coil is parallel to the magnetic fields, that's when the magnitude of the alternating current generated is the highest because it'll be moving to cut the magnetic fields perpendicularly. That means that at time equals 0, the magnitude of the AC would be the highest. So we do not start from 0, we will start from a point, let's say at the top over here. The value doesn't matter because there is no value for the voltage given, as long as you draw the peak at 0. Now what's the time period for 1 complete revolution? They told us the generator makes 2 complete revolutions in 1 second. That means that you need to draw 2 complete waves from 0 to 1. So 1 complete revolution must be completed within 0.5 seconds. So the sinusoidal wave will start from the top here. I'm going to do my best to draw it as correctly as possible. So the wave would start here and it needs to make one complete wave ending over here. The second wave would then go up to here. So this is the halfway point, which means that the maximum negative should be between 0 and 0.5, which is 0.25. So we're going to start from here. We'll make one complete wave from here down and then up. I know my drawing's pretty terrible. Please do a better job than me. And then we're going to draw another wave here to here. So now let's check the mark scheme to see how we can score the 3 marks. So they told us the graph is sinusoidal with a positive and negative EMF. So we have positive and negative EMF. That's 1 mark. So I'm going to put 1 tick to indicate 1 mark. Another mark is given for showing a minimum of 1 cycle, which is completed in 0.5 seconds, and that's what we got. So that's another mark. The third mark is for putting the EMF at a maximum of 0.00 seconds, curving to a minimum at 0.25, and curving back to the maximum of 0.50, which we got. Or you can even start from the bottom here. That means if you go the other way, it also works. Because as long as you start from a maximum value, so this is the maximum negative, you can even start from here as long as you show one complete wave in the same time period of 0.50 seconds. That's why even if you draw it as a mirror image starting from the bottom, it still is accepted. So that's how we score the 3 marks for this question. C. In power stations, transformers are used to step up the voltage of electricity generated before it is transmitted through cables of long distances. 1. Explain the advantages of transmitting electricity at high voltages. So if you can recall, the reason why we transmit electricity at high voltages is because there's less power loss. So I'm going to write that here. You need to explain, which means you need to give the reason. This is because there will be less current flow. And the reason why this less current flow would have less power loss is because it is based on the equation for power loss. I'm going to write that here. Of power loss, which is, I'm going to write it out because this tool doesn't allow us to do superscript or subscript. So I'm going to write here P equals I squared R. So based on the equation of power loss, lower current will have less power loss. So why we need to write the equation is because we need to show the relationship between the high voltage, less power loss, less current flow. So that's why I've written it this much. So let's check the mark scheme. So to get the 2 marks, you can either write less power loss, which is what we did, and you should also include the equation of P equals I squared R. So that's how we can get the 2 marks. Now, besides writing this, you can also write that there is lower current, and this has to be accompanied with the use of thinner or cheaper cables. So they accept this answer as well. Just that for me, I prefer this answer because one of the main reasons for this transmission at high voltage is because we want to reduce power loss so that there's no unnecessary wastage of the electrical energy. So that's for 2 marks. Now, if you only wrote any one of the following, that means you wrote less power loss, P equals I squared R, low current or thinner and cheaper cables without the matching explanation, you'd only get 1 mark and not the full 2 marks. 2. A power station generates electricity at 25,000 volts. A transformer steps up the voltage to 300,000 volts. The primary coil of the step-up transformer has 450 turns. Calculate the number of turns NS on the secondary coil of the transformer. So I'm going to use the ratio of the number of turns on the primary to the number of turns at the secondary, and it is equal to the primary voltage ratio to the secondary voltage. So all we need to do is just substitute the values in. NP is 450, NS is unknown because we're looking for it. VP is the primary voltage, which is 25,000 volts. And the secondary voltage is 300,000 volts. Working this out, you'll get a number of turns on the secondary coil as 5,400 turns. That's the answer we will write in the space provided. So now let's check the answer scheme. Yes, 5,400 is the correct answer. So if you get the correct value, there are no units for number of turns, so no units is necessary. Getting the correct number will score us 2 marks. But remember, we always want to write the working just in case we make any calculation errors. So let's say you didn't get the answer of 5,400. You can still score a mark if you wrote the correct equation, or a rearrangement of the same equation, or if you have the correct substitution. So sometimes it can happen where all the substitutions are correct, but you key the numbers into the calculator wrongly and you came out with the wrong number. So that's why it's very important to show your working, so that just in case your final number happens to be incorrect, you can still get a mark for the correct equation or the correct substitution. And that's how we solve question 8. If you found this video to be helpful, click like and subscribe. And do let me know how you have found this video to have helped you. To watch videos on other questions, check out the playlist on my YouTube channel or on my website physicsrocks.com to find the question that you are looking for. If you have any requests for a particular question, drop your request in the comments below, stating the year, month, variant, and question number. And if I haven't covered that question yet, I will do my best to come up with the explanation video as soon as possible. All the best for your examinations!